is n equal 1 to infinity of n squared divided by e to the n over 3. Can we use the integral test? Okay, I think we can. Now, can you prove to me that the conditions of the integral test and the hypothesis of the integral test are satisfied? So positive, decreasing, continuous. So positive, kind of easy. Okay, I'll buy that without much discussion. Okay, I'll buy positive. Okay, what about continuous? I'll pretty much buy continuity if you cite a known Calc 1 theorem. So what Calc 1 theorem would you cite for continuous?
Epsilon.
Well, is this a continuous function over this
Yes.
interval? And is this a continuous function?
Yes.
So quotient of continuous functions where the denominator is non-zero, that's a Calc 1 theorem, will be continuous. So I'll buy continuity. What about decreasing? You might have to convince me of decreasing. Is it decreasing?
Yes, because E is bigger than n squared.
Yeah, that's kind of the argument. But it's not totally obvious, right? Because if you say, okay, n plus 1 squared and e to the n plus 1 over 3. Now this is larger than that, but the numerator here is also larger.
Can we plug in a
But
billion?
you're going to kind of argue that, yeah, it's not as much of a difference, and I agree, but what's the Calc 1? First derivative. Let's do a 1D test and nail it down. So all we have to do is take a first derivative test, show that the first derivative is negative, and that will show decreasing. So we just have to take, for f of x being x squared, e to the minus x over 3, and we just have to take the first derivative test and see what we get. Okay, so it's going to be a easy product rule, right? So what's the derivative?
2x.
Okay, 2x times e to the minus x over 3 plus x squared times, there's a little change over there on the sub expression. What's the derivative of e to the minus x over 3?
The negative 1/3.
Minus 1/3, yeah. So we're going to get e to the minus x over 3 times minus a third. Or in other words, we're getting 2x e to the minus x over 3 minus x squared over 3 e to the minus x over 3. We could factor this, or factor it out and actually put it in the denominator. And then what do we have left? We've got 2x minus x squared over 3. So certainly this is going to get negative once x gets big enough, right? Because we can factor this to x to 2 minus x over 3, right? And so from 1 to infinity, this is going to be positive, this is going to be positive, but after you get to what? After you get to beyond 6, this is going to be negative. And we only care about the tail of the series. In other words, you could have asked the question about starting at 7 and run the integral test, so this will be negative, it will be decreasing. So
But if you had like 2 negatives, then it would be decreasing or?
Well, it depends what you get. I mean, this is,
No, but how does this plus and minus thing work? So
well, I'm just saying,
if
this is positive, this is positive, this is negative, so the whole thing is negative.
if you had two negatives, then it'll all be positive.
Yeah,
Okay.
well, you know that. You know negative times negative.
Oh, so you're multiplying.
Yeah. So positive times negative divided by positive, it's negative. So this is going to be negative. These will stay positive. This will be negative after 7, right? Once x is greater than or equal to 7. So you can integrate it, therefore, yeah? So you can integrate from 7 to infinity, and you could do x squared e to the minus x over 3. How would you integrate it? What technique would you use here? Parts, yeah, do parts. So let's do parts. So let's make a parts box. Let's do x squared e to the minus x over 3. This is going to be what? What's the antiderivative?
Negative e over 3 to the x, negative x over 3. Negative 1/3 times e to the
Negative 1/3?
Oh, negative, sorry.
What's the compensation?
Yeah, sorry.
Oh, 1/3.
No, it's 3.
3.
Negative
3,
Yeah,
the antiderivative,
Right,
right?
yeah.
So you have to have minus 3 e to the minus x over 3. So, because when you differentiated this, that minus 1/3 would come out, but then it would be balanced by this. So that would be the antiderivative. That would be g. Here's g prime. F prime would be 2x. Okay, so what I'm getting is minus 3x squared over e to the x over 3 minus a minus, so it's plus 6 antiderivative of x e to the minus x over 3. And now one last parts box here. So x1 e to the minus x over 3 minus 3 e to the minus x over 3. And so here we are getting a minus 3x e to the minus x over 3. And then minus a minus, so it's going to be plus 3 antiderivative of e to the minus x over 3. Okay, so what are we getting? Let's get some more root. What are we getting with this? Minus 3x squared over e x to the 3. And I'm getting a minus 18x and then lastly, when I integrate this, I get this, so I get a minus 9. Okay, so my antiderivative, putting it all together, here's my antiderivative. Okay, I evaluate from 7 to t and take the limit as t gets big, and yeah, you'll have you could do a L'Hopital and you'd see that it went to 0. Does everyone see that? This is going to dominate this, right? If you do L'Hopital twice, you'll force this to be a constant. This is still going to remain exponential. So then it'll go to 0. Just do L'Hopital's rule 2 times. Yeah. So this is a negative infinity over infinity form, so you can do L'Hopital's rule. So if you're doing a limit as t goes to infinity, so when you do L'Hopital's rule the first time, you're going to get a minus 6t minus 18 over e t to the 3 1/3 e to the t over 3. But this is still going to be a negative infinity over infinity form when t gets big. So you do L'Hopital one more time, and then you get minus 6 over e to the t over 3 times a 9. And now t is still getting big, and this gets incredibly big. So it's negative 6 over huge, which goes to 0. So that piece will go to 0, and then you'll get the convergence there when you throw in the lower term. Okay? So, yes.
Like, so it converges at 7? Or whatever you get from
Well, yeah, I
7?
mean, that part's going to go to 0, and then when you have to subtract what it is at 7, so you're subtracting minus 3 times 7 squared minus 18 times 7 minus 9 over e to the 7/3, but this is just a finite result, right?
And that's the answer.
So well, that would be the answer to the integral. But we don't really care. We just care that the integral converged, right? So as long as it's a real number, remember the series isn't going to converge to necessarily the same real number that the integral is, but there is the relationship that it will at least be finite. The series will be finite, and that's all your answer.
Do you have to find out where it converges?
And then you just have to say it converges. Your answer will just be converge. Yeah. There's only a few that, like I told you that series 1 over n squared converges to pi squared over 6. The geometric ones you can figure out exactly what they converge to because you have the formula like a over 1 minus r. You have the telescopic, you can figure those out. Yeah, so but most of them you're just going to say they converge. Right?
Okay.
Converge or diverge. All right, so I think those are some good problems, yeah. That was a good problem.
That was a hard problem.
Yeah, that was a mess.
Yeah, some hard problems, you can do the easy ones.
Did you do parts 2 times?
So, I'll talk about the ratio test, and then I'll talk about the ratio test some more on Monday. Okay? So 2 things. Also, I want to talk about absolute convergence. So we're going to say that a series converges absolutely when the series, if you put the absolute value here, when this converges. Okay, so that's absolute convergence. So for instance, it's going to turn out, we haven't shown it yet, but we will, that if we put a alternating sign, so if I put an alternating sign with 1 over n, it's going to converge. But it would not converge absolutely. So we call this conditional convergence. So in other words, this is what? 1 over n minus, this is 1 over 1 minus 1 over 2 plus 1/3 minus 1/4 plus 1/5, etc. This is, we're going to see later this converges, but if you took the absolute value and just looked at, so if you look at this, which is just your series 1 over n, this diverges, not by the integral test. So that's not a absolutely convergent series. Now, absolute convergence is stronger than convergence. In other words, if a series if you take the series of the absolute value and those converge, then certainly the series of the a sub n will converge. Okay.
What does that say?
Oh,
And And the way that you can prove that is by a comparison test. Okay, so a sub n let's see, so I can look at, if I take the absolute value of a sub n, and I look at, well, here, let's say, okay, so I could start there, and then I could add absolute value of an to both sides, to all sides. So I could get 2 absolute value of an is greater than or equal to absolute value an plus an, and greater than or equal to, this will be 0. Okay. And so if this series converged, well then, certainly just throwing in the constant 2, it's still going to converge. And if this converges, we know that this series will converge. And if this series converges, given that this converges, we now know that this series converges. So that would be the argument. Okay, so absolute convergence stronger than convergence. If a series converges absolutely, it will certainly converge. If a series converges, it doesn't mean that it converges absolutely. Okay, and now I'm going to do the ratio test. So, did everyone have this? So we're just doing a comparison test. This is larger than this. If this converges, then the series of this will converge.
So if the series converges absolutely, then the series will
Yes, converge, yeah.
What is the third called?
Absolute convergence plus convergence. So let's look at a ratio test. Now the ratio test, you're going to have a series AN. Again, these are positive terms. And you're going to take the series ANs, we're going to take a limit as n goes to infinity. So you're trying to see, does this converge? And you're going to take a limit as n goes to infinity of the n plus first term in the sequence that is generating the series, divided by an, the nth term. Okay? So you do the ratio. That's why it's called a ratio test. Okay? And 3 things can happen. Here, 1 is the cutoff. 1 is the important number to remember here. So it's different than the limit comparison test. If it turns out to be 1, you get no info. If you take this limit and it is less than 1, you get info, you get convergence. And if you take this limit and you get greater than 1, you get divergence. that's the ratio test. And a ratio test, we'll do an example with factorials to show you how to handle factorials with a ratio test really easily. Okay, let me give you a quick justification for this, and we're going to use our geometric series knowledge here. Okay, yeah, actually geometric. Okay. So, let's say that the limit as n goes to infinity of a sub n over a sub n plus 1 is equal to, is less than 1. So therefore, we could say, well, it's going to go, what does that mean? What does that mean? It means that it's going to it means that it's going to R, and R is less than 1. Some R that is less than 1.
R being constant.
I mean, it's going to have a limit, right? It's going to go to, it's going to actually, I mean, this limit is going to be converge to something R, which is less than 1. Okay,
so
but
since
what?
it converges, we know that the rate has to be less than 1.
Hmm?
So from the test, we know it's going to converge. And
The
from that,
series, but we're talking about the sequence, just the sequence.
yeah, but since it converges, we know that the sequence that R must be less than 1.
Yeah, because we're in this case. I'm
Yeah.
doing this case. I'm doing this case.
Oh.
Okay? Now, I want to justify this case here. Okay? So, what we're going to do is, what does this mean? Let's think about what this means. What does this, let's go back to epsilon, the end definition. What does it mean? Let's try to figure out what it means. So it means for every epsilon,
Less than 1.
there exists
R.
a big N, right? Such that what?
N is greater than another one.
Such that the absolute value of, such that if little n is greater than big N, the absolute value of, well, that ratio. So a sub n plus 1 over a sub n minus what?
R.
Minus r, okay, will be
Less than
less than
1. N.
less than what? Epsilon. Okay? In other words, a sub n plus 1 over a sub n will be less than r plus epsilon. Okay? Now, we want to choose, we'll just, wherever this r is, right, here's, just look on the number line, so here's, say, 1, and here's r. Okay? Choose your epsilon small enough so that r plus epsilon is still less than 1. Okay, so this would be like r plus epsilon, for epsilon small enough. Call this, I don't know what you want to call this, let's call it B, okay? Okay? So B is just representing r plus epsilon. So in other words, what we've got is that a sub n plus 1 over a sub n is less than b, which is less than 1, right? And greater than 0, right? so this for little n greater than big N. Okay? So in other words, let's look at n plus 1. Big N plus 1 is certainly greater than big N. So I can say that A big N plus 2 over A big N plus 1 is less than B, right? I can certainly say that. Well, let's move this to the other side. So A big N plus 2 is less than B times A big N plus 1. All right, well, let's go one step further. What about N plus 2? That's also, big N plus 2 is also bigger than big N. So I should be getting that A big N plus 3 over A big N plus 2 is also less than B. Or in other words, A big N plus 3 is less than B times A N plus 2. But A N plus 2 is less than B times A N plus 1. So this is less than what? B squared A big N plus 1. Okay, do you see what's going to happen? And so you continue. A N plus 4 is going to be less than B cubed A big N plus 1, etc. And so now you take this series. Now you add these up. Okay, and then you look at this series here. And you see how that's geometric?
Why did you square? Why did you square B?
Because I've got B here, but B times this, but this is less than that, so I'm substituting this in here, I'm going to get a B squared.
Oh.
And the next time I substitute it in, I'm going to get a B cubed. Right? Did everyone see that? It's going to keep going like that. So in other words, this series, you could use a comparison test, this series A sub big N plus K, for say K equal 2 to infinity. In other words, this is the tail of the original series that we're looking at. This is going to be, we could say this is going to be less than, certainly less than or equal to this series right here, which is just B to the K for K equal 1 to infinity. And this will be A sub big, what are we, this is just A sub big N plus 1, okay, which is just a constant. All right, so what am I getting? Geometric series, right? And we know it converges. We know that this converges because the absolute value of B is less than 1. So therefore, this converges by the comparison test. So you are using you're using geometric series knowledge here. Okay? Okay, so that's the justification of the ratio test. Let's see where we use it. Okay, so let's see where we use it. It's like every time on Friday I'm going, oh, it's like every Friday, the last 3 Fridays, I'm just having migraines at the end of the week. I don't know why.
Too much calculus.
I don't know.
Too many students.
So let's do one with let's try one like series from n to n equals 1 to infinity of 7 to the n divided by n factorial. Okay, does this converge? All right, here's your factorial. This would be really good with a ratio test. So what you can do is say, I'm gonna run my ratio test. So I'm going to take a limit as n goes to infinity of 7 to the n plus 1 over n plus 1 factorial divided by 7 to the n over n factorial. And what's going to happen? This is going to flip, so this is going to be n factorial 7 to the n. This is going to cancel and just create a 7 here. But what is this? N factorial cancels and just leaves the n plus 1. Does everyone see that? Because n factorial over n plus 1 factorial is n factorial over n plus 1 times n factorial. These cancel. So you're just getting 1 over n plus 1. So what we're getting here is a limit as n goes to infinity of 7 over n plus 1. That's 0. 0 is less than 1, so converge by the ratio test.
Wait, could you explain where you canceled again?
Yeah, how did you cancel
So
the, cancel the n?
n factorial divided by n plus 1 factorial. Remember, n plus 1 factorial is the same thing as n plus 1 times all the others, the n factorial. Like 7 factorial is 7 times 6 factorial, right? So n plus 1 factorial is n plus 1 times n factorial.
Right.
So these now cancel, and you're just left with 1 over n, or you still got the 7. N's getting big, this is going to 0, so ratio tests converge.
But wouldn't the top n factorial cancel out with the bottom one? Or cross multiply?
No, the n factorial divided by n plus 1 factorial just leaves n plus 1 in the denominator.
Yeah, I get that part, but the top one wouldn't cancel with the one.
Well, you've got 7 to the n plus 1 over 7 to the n. The only thing that's left is a 7.
Yeah, I get that part too.
Okay, so you've got 7 divided by n plus 1. That's 7 over huge. N is getting big. So this is going to get smaller and smaller and go to 0.
Yes, I did
Did
that
you
one.
mean this one right here?
Which one?
Right there, right there.
I get the whole,
Right next
why
to the
they
huge.
cancel.
Over huge, yeah.
Next to the 7 over huge.
Yeah, right?
Cause,
This?
yeah.
Yes, that's what she.
Yeah.
I was
This
thinking,
is
wouldn't
going
that
to be 1 over n plus 1.
Yeah, but wouldn't that cancel out with that n
Cancel out
factorial?
what? That's what we have. I'm just repeating what we had here.
Oh, okay. I get that.
Yeah, I'm just putting it on the side.
Okay.
Yeah. Okay. Yeah, I was just, because you were, someone was asking, right? How did you get that? So I was just explaining it on the side. Yeah. Yeah, this is just another explanation of what I was doing here.
Okay.
Yeah. Okay, so there's an example where the ratio test is really good. Okay, what about, let's do another one. We got 5 minutes left, let's do one more. Do it.
There's just so much canceling. So.
Okay, that's what I need.
You don't have to, sorry.
That's why I didn't do that. It was 7 right off the bat. Oh, 7 to the okay.
That's why.
With this one. Because you're dividing this whole thing.
Okay, n factorial over 2n plus 1 factorial.
Yeah. This one.
No. And he's repeating this. Is,
Okay,
he just
does
does
this, can we run a ratio, let's run a ratio test. So tell me what, I'm gonna run a ratio test here. What am I going to be essentially, what limit am I gonna be taking? Tell me what limit I'm taking.
limit into infinity of,
Of what?
2n plus 1 to n.
Well, give me I'm gonna take the
no.
n plus first term, which is what?
So it's n plus 1
N
factorial.
N plus 1 factorial
Factorial.
over what?
2n plus 2 factorial?
No? 2n plus,
Oh, 2n plus 1 plus 1 factorial.
2n plus 3 factorial,
What?
Oh,
I
yeah.
don't understand.
right?
What did it be two?
So
No,
2
you have to add
times n
plus
plus
one to
1 plus
Oh,
1
okay.
And then you multiply
is
2
2n plus
and
3,
plus
right? Because of this.
Oh.
So this is gonna be 2n plus 3 factorial, right? And now you're gonna be dividing by this. Does everyone see that? That's the ratio test, okay? You plug in n plus 1, and then you divide what happens when you plug in n, right? So in other words, you plug in n plus 1 and then divide by this thing itself. Now, that's gonna flip it. So let's put our 2n plus 1 factorial up here and put our n factorial here. Okay. Now, do you know the cancellation? The n plus 1 factorial divided by n factorial is what? What's this divided by this?
N factorial.
n plus 1.
N plus 1.
Oh, because we took away the factor.
Just n plus 1. Question, what happens when you take 2n plus 1 factorial and divide by 2n plus 3 factorial? What's left?
2 and 2 is 2.
remains 2.
2n plus 2 times,
Factorial?
no?
N?
2n plus 2 in the denominator, you're going to have 2n plus 2 times,
2.
Wait,
don't get
yeah, let's
it.
try that.
So
no, look. Look,
I started.
what is 2n plus 3 factorial? Here's 2n plus 1 factorial. What is 2n plus 3? It's all the numbers 1, 2, 3, all multiplied